those who weren't there at the beginning, my name is Bimbard. I'm a postdoc in the Carnegie Harris Lab at UCL. And along with Marius Bauza, who's also in UCL, we're going to talk about chronic neuropixels recording. And just a definition, what we would call chronic is basically when the probe is implanted on the head of the animal, and it lives on the animal, and you can recover it or not. But it's not like the acute, where at the end of the day you have to remove your probes. Okay, all right. So just a very brief outline. So I'm going to talk, briefly introduce the techniques and talk about why you may want to do chronic, then talk about the general principles of the chronic implantations, mainly in mice. And then I will highlight a few of the challenges that I think we are still facing, and it can be, interesting work for future. And then Marius will take over to talk about the general principles and the techniques in rats. All right, so why would you want to do chronic recordings? I think there are three reasons you may want to do that. The first one, it's kind of obvious, is to record from freely moving animals, as was done here in this paper from the Churchill lab, where a mouse has been implanted with Neuropixels. It can move around, you can record at the same time. That can be pretty interesting if you're interested in natural behavior, for example. The second thing, which is a bit less maybe obvious, is that as Carolina mentioned in her first talk, the probe, you can only record 384 channels, especially on the, for example, on that example of 4 Shanks 2.0 neuropixel. You can only record a subset of it. And so if you want to record along the whole probe, because you're interested in brain-wide activity, you will have to do it on different days, right? So in acute, it would take a long time, but if you do a chronic prep, you just do it once, and then every day is just 5-minute preparation. And this is, for example, the spiking activity along the whole of the probe. It's like more than 800 neurons recorded there. And finally, as Matteo also mentioned at the beginning, one thing you can be interested in is to record the brain activity across time. For example, if you're interested in learning. So this is here showing the number of neurons recorded from one probe across many labs. Each color is a different lab, and each set of dot and line is actually a mouse. And this is the number of days since implantation. So you can record for days and days. In that case, it ends at 60 days, but some of these people here have been recording for more than 100, 200 days. And the idea is to keep track of the same population or even the same neurons across days. All right, so there are two main approaches. The first one is a permanent implant, where you cement the probe to the skull. And the second one, which I'm a bit more confident with, is the retrievable implant, which is basically based on specific designs, where you can recover the probe afterwards. So I'm going to briefly talk about how you can permanently implant a probe. Basically, the very beginning is the same as what Severin and Carolina just talked about, which is acute insertions. You put a head plate on the mouse if you're interested in doing head fix, or you do a craniotomy on the skull to expose the cortex or the brain in general. Then you insert your probe, and so far, that's what you do in acute. But then at that stage here, you may put some silicone on top of the brain to protect it. And then actually you're going to cover the whole thing with cement to, stabilize the whole probe in the brain. Okay. So then this is, again, a permanent implant. You can't really recover that. So then the probe is implanted. You may protect it with a little protector like this, where that can hold, for example, the flexes and the head stage and so on, if you're interested in especially freely moving. And then, as I said, the explantation process is basically none. It's pretty hard to retrieve. You can try to drill it out, but that's not the easiest. The second type of implant are the retrievable implant, or recoverable implant, or reusable implant. And basically, they all come with the same kind of principles, different flavors, but always the same kind of basic principles. And to exemplify this, I've taken here the design from the Hessler lab, which is pretty cool. It's very well designed. And in that design here, you have 3 different parts. Okay, so you have the probe mount, which is that piece here, on which the probes are mounted. And in that case, even the head stage is mounted. This is the part that's precious, and that's the one you're going to reuse over and over. That part is connected to the skull connector by some screws that you can't see here. And in the end, only the skull connector is going to be attached to the head of the mouse or of the rat. And so that part is the part that you're gonna not reuse but change every time. That's gonna stay on the head of the mouse. And in the end, there's some protection to protect the electronics because, you know, when the mouse or the rat is keeping that thing on its head for weeks and months, you know, you get to protect it. And this is the design we have ourselves. So just to exemplify, you know, this is basically very inspired from this one. So in that case, you have a payload module here on which you can put 2 probes, which are protected by lids. And this whole thing that you reuse every time is then docked to a docking module that's going to stay on the head of the animal. All right, so the thing is, if you want to, you know, combine these two things, the probe mount and the skull connector, I mean, they have slightly different names, but the payload module and the docking module, sorry about that. You get to be pretty careful because, you know, the probe is mounted on there, so you can't do it just by hand. So most of the time there's a contraption that you can use to do that. So in that case, we're just showing the one I'm just showing the one we're using. This is here the payload module on which the probe is mounted. And here docking module, and just want to assemble these 2 pieces. And basically the way it works is you're going to slide those pieces together along the poles that you can see here. And because the poles are well aligned, then you can slide it in pretty smoothly without any risk of breaking the probe. So now I'm going to go over the implantation process. I'm going to, you know, skim through it quite quickly. I think Maya's going to spend a bit more time on this. But basically the way it goes is, again, same kind of thing as what happens for the acute. So you have your brain. In that case, let's say we were interested into implanting 2 probes in the frontal cortex of a mouse, which is here the secondary motor cortex in green. So there are 2 holes because I've just done a craniotomy. I'm putting some Duragel, as Caroline explained, to protect the brain and keep it moist. Then inserting the probe. You may think it's huge, but actually I think I did not screw up the scale on this one. It's just that the mouse brain is pretty small. And in that case, this is the tip of the probe, if you can see my cursor. And you can't have something much smaller because the whole of the shank and then the electronics goes up to there. So this is, you know, the kind of the minimal size that we try to come up with. Okay, so now that it's in the brain, this is the kind of thing that you can get. You have here 2 craniotomies. This is a view from above. This is the over the frontal cortex and then somatosensory cortex. And you have 2 probes here with 4 shanks each that are going to the brain. And, you know, as you're going in, the 2 probes, sorry, are coming in together. So you increase the chances of having one shank that's bending and so on. So you have to be careful at that step. Okay, so now that everything's been inserted, you can cover the whole thing and protect it with UV cement. That is usually pretty practical because it's pretty thick, so you can manipulate it easily. And then you cover the whole thing with dental cement, and then you're ready to go. The mouse is ready to roam around in its cage or do whatever it likes. And the explantation process, so that's the whole point of these implants. Basically, you come up from above. After a month or 2, when you're done with your experiment, you attach some payload module holder to the payload module. You unscrew the screws here. Most of the implants have some screws. And then you can finally retract the payload module, clean it, reuse it for the next mouse, and then you leave the docking module, which is this piece here, on the head of the mouse, and this one you can't really reuse it, but that's okay because most of the time it costs like £3 and it's 3D printed. Okay, so some issues that can happen. The first one is during the implantation process, or rather during the building process, building the implant. Sometimes the probes aren't straight. It can be pretty hard, especially when you have 2 of them, to have them exactly straight and you know, with the right angles. I think the Hessler lab has a pretty cool contraption also to align it. But this can happen, so you get to take the time because then possibly you're going to reuse the same implant for month and month. It can also be the insertion is difficult. As Carolina mentioned, you get to keep the brain moist, first of all with Duragel, because as soon as it dries up, usually it thickens. And then during the explantation process, a few things that we've noticed, sometimes it can be pretty hard to explant, and this can be due to some issues in the alignment and some mechanical friction that's making it pretty hard to remove the payload module from the docking module. And another issue can be that the probe is dirty. As you can see here on this image, this is pretty dirty. It's upside down, so the 2 probes are here. You can see 8 shanks if you have very good eyes. But on top of these 8 shanks, you have plenty of dust and residues and so on. So this can happen because of several things. It can be the Duragel that dried up and sticks to the probe. It can be some dust that got in. So usually the best way is to prevent that from happening in the first place by filling in any gap that you may have in your implant. And then if it happens anyway, you can wash it with tergazine, then some bath of deionized water, or even use stronger solvents. So I've talked about a few implants here, but there are many types of implants with all have their own characteristics. So for example, this one from the Churchill lab is very lightweight. This one from the Brody lab is very used for rats and so on and so forth. I've listed a few here. I think there are more, and I'm sorry if I'm missing more. But definitely I've listed here a few characteristics that I think are important to take into account when you're planning your experiments. The first one is the weight. I think I had the right numbers here for these weights. So you have some of them that are pretty lightweight. This one's been specifically designed for that, has other drawbacks, but yeah, that's one advantage. And some others that are more heavy, but they might also be a bit more sturdy. So weight is one thing, sturdiness, stability. Can you do freely moving? I think all of these guys you can do freely moving with it. These guys not yet. Is it easy to retrieve, and so on and so forth. So you may want to consider these questions before starting. Finally, I'm just going to highlight a few of the challenges that I think we're still facing, and that it's important to know before starting your experiments. The first one I think is stability. This is the kind of plot you've seen already. So this is the number of days since the implantation. This is the number of units per electrode. It's just a value for the neuron count. And what happens, what I've seen, and I think other people have seen, is that most of the time you get this decrease at the beginning, and then it stabilizes. And this can be due to many things. It can be due to damage to the brain, to glia, getting on your shanks. We don't know really, but it's pretty hard to not have it. And there's this pretty cool study from the Brody lab by Lou and Bondi, who investigated whether it depended actually on the region. And they showed that whether you're recording cortically or subcortically, you may have a higher decrease in cortical areas than in subcortical areas, but also whether you're recording at the front or at the back of the brain, where the front of the brain is more stable. And actually in our own recording here in the lab, recording from superior colliculus is pretty hard. You lose neurons very rapidly compared to frontal cortex. Another challenge that Matteo mentioned at the very beginning is to track neurons. So there are several ways to do it. One way is to spike sort, as you'll see in the next talk, or the coming talks, spike sort all the recordings together so that the algorithm can find the same neurons over days. But even doing that, you may want to have a proof of, Anna Lebedeva, especially in this lab, was interested in having a proof of concept of how stable those recordings could be. And she used a fingerprint, and she made use of the fact that visual cortex has neurons that respond very specifically to specific images. So you have here 3 different images, and the response of here a single neuron. So we can see it responds differently to each of the image. It has a specific signature, but this signature is stable across days. So if you record on 3 different days, which are indicated by the color, you keep the same kind of signature, and it's the same for the second neuron. So using that, she showed that she could actually record from the same neurons across weeks and months. And so that's pretty cool. You may not be able to do the fingerprinting thing when you're recording outside of sensory areas, but here the idea was to prove that for that kind of implant, you get pretty stable recordings. We've tried it with the retrievable implants. What you see here is basically the number of days between the 2 recordings, and here the number of stable neurons in V1. And even with the retrievable implant, we managed to get a population of about 100 neurons that we keep for a week. Usually then it decreases, it's pretty hard to get, but yeah. So stability was one thing that I think where there's plenty of improvement to be made that can be good to address specific questions like learning and so on. Another one that may arise is also the flexibility. If you want to record, for example, from auditory cortex, it can be pretty difficult because it's on the side, and having this big thing sticking out of the mouse head may not be possible. We still tried to design, in that case, docking modules that have different angles. So you may want to play with that. Also different heights if you want to record in shallow regions or deep regions, and also different spacings if you want to record different areas, multiple areas that are far apart or very close apart. But in any case, with chronic recordings, the number of probes per implant is quite limited. Some implants, especially in rats, have managed to put more, like up to 4 probes, I think. but also geometry is fixed. So you can't go, just like Severin showed, in many different places to explore the whole visual hierarchy, which is pretty cool. But doing that in chronic is much harder. And with that, I'll just conclude. I think one of the very important things to do before starting is really ask what are your needs, in which species you want to do it, in which brain region, for how long, what is the angle you want to use, you want lightweight, and so on. So there are all these questions that are very useful to think about before choosing and picking the proper implant. And then the main challenges, at least in my opinion, are technically keeping the same neurons over time is still quite hard for retrievable implants, and that means there's a lot of room for future improvements. And also on the computational side, tracking those neurons and spike sorting all decisions together is something that's been going on. And for example, for pi kilosort, maybe Alessio is going to talk about it later. Yeah, so that's it. Just a little acknowledgement slide, and then I think Marius, you can take over.
Hello, can you see my screen?
It's all black for now, but I think now it's good.
All right, let me find it. Can you see my cursor? Can I just get? Yeah, can you see it?
Yeah, that's great. Thanks, Marius.
So thanks, Cillian, for telling us about mice implants. And the introduction. I will talk more about the details of how I do and what I do in rats. So I work mainly in rats, and with Neuropixels, I work only in rats. And of course, there are a few differences between the mice and rats. Some of them are good, some of them are not that good. So you have more space on the head, they're much bigger, so you can plan much better the implants. And the implants also can be bigger and heavier. On the minus sides, we have much better protections. So rats are really strong and they can just grab the implant and just pull it off. That's why we need very good protection, very good covers. Also, we have more brain motion. They move a lot. They can bang their heads in the walls. They can grab their heads when they clean. It's also, the brain moves quite a bit. And you can actually observe that in the implants. And you need to ensure that stabilization is really good. I typically implant two Neuropixel probes, either 1.0 or 2.0, which is for shank, and I implant them in two areas. So I record simultaneously from hippocampus and entorhinal cortex, and I implant a hippocampus one straight and entorhinal cortex angle. And for that, I'm using the probe, one of the probes that Cillian showed already. So this was developed together with Yoiso Guy and Daniel Register from SWC, and it consists of 3 parts. So it has a body probe holder body A, legs B, which would be very similar to what Cillian showed before, and I have adapter C. So how it works is I glue probe into the holder A. Sorry, that was supposed to be A. And I use 2-part epoxy. So you need to align carefully and glue it with epoxy. Then I put it on the legs B and I have screws on the sides. So to make sure that it's well connected. So it's 2 or 4 screws. It's never really moves once it's connected. Then I attach it with a holder C, which is a 3D printed holder. And then it becomes really very similar to tetroid recordings and tetroid implants. And you just use stereotactic arms to manipulate, to change the angle of the probe, to change the position, change the orientation, and so on. I use 2 stereotactic arms. And with this setup, because the holder C is very small, I can just go very close with them at different angles and so on. So it's really is a big difference compared to mice, where it's difficult to have different angles at the same time. So once I am happy with the position, I insert the probe, cement everything, undo the screws on C, and once I remove that, the implant stays. So the implant, as you see here, is really small, it's well under 1 gram, and it's really well fixed. And during recovery, because all of them are recoverable probes, I go back to stereotactic arm, attach it to again the holder, undo the screws on the sides, and then you can just lift off from the legs the probe, and it's explanted. That's it. And typically, almost all the probes from Neuropixel 1.0 are recovered, and most of the probes from Neuropixel 2.0 are recovered in this method. You need, of course, to do some preparation, maybe put some Vaseline on the legs, but once it's there, it just slides out very smoothly out of the brain. And the implantation procedure is as follows. So it's very similar in a way to what you already saw in the previous talks. Just a few details that I do for preparation. So one thing, I always prepare probes with Vaseline before the surgery. So day before or something like that, I come to lab and I put molten Vaseline on the probe base, covering the part of the probe shank that is not going into the brain. And I use melted Vaseline because if you do it during the surgery or use not molten Vaseline, issue is that often you have small crevices left. And what happens or might happen is through these crevices, your cement might leak in, and once it's drying, it's because of the heat and the movement, it might touch the probe, and if it's touching, it's more likely than not that the probe will be dead. It will be broken. When I do surgery, typically I remove or slice dura. So in the above entorhinal cortex, you always have to remove the dura. You can't leave it there. But above hippocampus, I just use 2 needles. So I just lift the dura up slightly, made incision to make sure that it's enough to put the probes in. And in this way, I never had issues with insertion of a single shank or 4 shank probes in rats. And the rest is as you would do in normal probe or tetra recording. So you do your screws, I cover the skull with Metabond to ensure that they have better connection, and so on. Same as Corlina and other people, I use artificial dura or a dura gel, which the brand is shown here, to cover the brain. So I insert the probe, cover the brain with artificial dura, make sure that all the edges between the Vaseline and the dura are covered, and then I just cover it with Vaseline up to approximately here or so, and that means that this probe, this insertion site is fully protected. And in rats, very importantly, once I do that, I put on the copper mesh protection. So it is it's just really a copper shield that's sitting on the brain and fully encapsulating the implant. And I use it for both protection and head stage attachment. What that means is that I just clamp the head stage in my recordings on this metal mesh, and that ensures that there's no force whatsoever on the implant itself. So because obviously, if you put force on the implant, you move it even a little bit, the probe will move within the brain, and that will increase your gliosis. So that's basically is never a good thing. And this whole procedure works well enough to have chronic recordings in rats in very large environments for if implant was successful for multiple months. In single experiments, we are doing up to 3 hours of exploration. So that is for 3 living animals, that's really a long time. And we have pulley system to reduce cable pull. So it's made of fishing line. So when animal moves around, cable moves with the animal. And in this case, in this system, we never really had issues where animal couldn't explore this large environment because of cable rotation and so on. So, and this is even not using the accommodator. So these are how we do our implants and our experiments. And just want to thank my supervisor John O'Keefe, my collaborators Julia Krupic and Stian Burton, and of course all the Neuropixel consortium people who made this possible.